Okay, in this video I'm going to discuss state changes with the focus being on the energy required for state changes. Remember that a state change is the breaking or the formation of intermolecular bonds. Intermolecular meaning between molecules. So for example, when water becomes ice, this dipole-dipole interaction between the partially negative part of the oxygen and the partially positive part of the hydrogen, this bond becomes stronger. It gets formed into that crystal lattice that the ice is going to take on. So it's either the formation of these intermolecular attractions or it's the breaking of them. So solids have the most intermolecular attraction and gases have the least, or they're broken the most. Energy is required to break bonds, as discussed before. So if we're taking these two things that are attracted to each other away from each other, it costs energy. So it costs energy to go from a solid to a liquid or from a liquid to a gas. Energy is also released when intermolecular bonds are formed. So if you have a gas and it's allowed to condense into a liquid, it will release energy as it does that. The amount of energy required to go from a solid to a liquid, or you could say released when you go from a liquid to a solid per mole, is called the molar enthalpy of fusion. Similar but not the exact same, the molar enthalpy of vaporization is used to represent going from a liquid to a gas. So for example, when water is boiled, it goes from a liquid to a gas. That costs energy to boil that water, and the amount of energy per mole is the enthalpy of vaporization. We put a U right there in Canada, but this spell check typically goes with the American stuff, so I spelled it that way. So how can we use these? Well, we can use them to calculate how much energy is required in a simple state change. So if I have H2O going from a liquid to a gas, I have to put some energy in to make that happen. So I can calculate how much energy I would actually have to put in there. Here, E is going to depend on my amount of water, represented in moles, times the delta H, or the molar enthalpy of, because I'm going from a liquid to a gas here, vaporization. Again, I'm just looking at these molar enthalpies of state changes in a chart, and again, in the textbook I happen to be teaching with, that's on page 307. But for water to go from a liquid to a gas, the delta H is 40.8 kilojoules per mole. Still significant. You'll notice a little bit smaller than your typical chemical reaction delta H because the intermolecular bonds are not as strong as the intra, or the bonds that form the molecule, but there's still a substantial amount of energy. So I have 1 liter of water. So again, remember, 1 liter is equal to 1,000 milliliters is equal to 1,000 grams when we're dealing with water. My moles is going to be equal to my mass over my molar mass, which would be 1,000 grams divided by the molar mass of water, which is 18 grams per mole. I think this is 55.6. And so in 1 liter of water, I have 55.6 moles. So my total energy required to boil this 1 liter of water is 55.6 moles, because I have 1 liter, times the energy that it costs for the state change, 40.8 kilojoules per mole. So what I would have to put in 2,268 kilojoules of energy to boil that water. That's a lot of energy. You'll notice when you compare this value, the delta H of vaporization, to the delta H of fusion in the next part of this question, that state changes associated with solid to liquid don't tend to cost as much energy as liquid to gas. Remember, when material goes from being a solid to a liquid, that intermolecular force is weakened, but it's not broken completely. Alternatively, when it goes from being a liquid to a gas, we say that that intermolecular force is broken completely. So breaking it completely costs more energy than just weakening it or loosening it. So how much energy is released when you freeze 1 liter of water? So again, I can go through this whole process and figure out that 1 liter of water is the equivalent of 55.6 moles. Looking at my chart, my delta H for the fusion of water would be 6.03 kilojoules per mole. And because here I'm going from the liquid to the solid, that should be solid, then when I do that, that energy, this is a bond formation, so that energy is being released. Or my delta H should be a negative in this case because I'm going from a liquid to a solid. So the energy change of my products would be 55.6 moles times my delta H of negative 6.03 kilojoules per mole, which means my energy change, 55.6 times 6.03, is 335 kilojoules negative. So obviously much less than this 2,268. But also, the fact that it's negative means that the H2O liquid is going to a stabler state as H2O gas. And so when it does that, it's releasing 335 kilojoules of energy to the environment. So remember, state changes do represent the formation and breaking of bonds. It's just intermolecular bonds, not intra. It's not as strong, but still requires energy to break them or releases energy when they're formed. Fusion refers to changes between solid and liquid. Vaporization means liquid and gas. And when we're looking at these delta H's, we have to interpret their signs based on what's happening. If we're going from a liquid to a gas or a solid to a liquid, those are endothermic changes where energy is being put into the reactants. And so we get positive delta H's. Those require energy to cause that state change. Alternatively, if we're going from a gas to a liquid or a liquid to a solid, those are bond formation, releasing energy. So we use negative delta H's and we get negative amounts of energy. What really means is energy available to the environment or exothermic reactions.